Greetings, everyone. My name is Christopher Young, and today we will be discussing nuclear fuel reprocessing applications and their benefits. This project has been the collaboration of Josh Perkins, Jonathan Shuck, and myself. Now, our project is really about the future of nuclear power, both domestically here in the United States and globally as well. We really wanted to approach this with a reduce, reuse, and recycle mindset. In today's world, the domestic and political climate is very focused on renewable energies and green energies. Together, we have strived to uncover and present the ways in which our greatest source of power can continue to provide us not with just clean energy, but energy that everyone can understand and accept as renewable, clean, and green. Already, Josh has begun by discussing the basics of nuclear power, and many of the current methods employed in the acquirement of uranium used for fuel, as well as the ways in which we currently utilize that fuel. Then, John has also discussed what currently becomes of this fuel as a waste product. I will begin our journey today beyond our current methods, but instead focus on potential methods for the future. We will discuss new methods of obtaining uranium, new methods and alternatives to better utilize that fuel, better ways to reduce the waste of that fuel. And then, when I am finished, you will hear more from John about the fuel after we have spent it. So our first topic is the acquisition of uranium from the ocean. There is currently a race between China, Japan, and the United States to determine who will be the first to create an economic solution to this environmental issue. And while this technology is not yet fully matured nor fully ready to compete economically, uranium extraction from seawater makes nuclear power completely renewable, with an almost complete reduction in negative environmental effects. Natural Resources Canada says renewable energy is energy obtained from natural resources that can be naturally replenished or renewed within a human lifespan. This is exactly what we will be discussing. Terrestrial uranium is the uranium that we currently mine from the Earth's surface. Above water, that is. As a mined resource, we are very limited in the amount of uranium that we can obtain. At our current demand, which we will discuss in greater depth, we have only enough terrestrial uranium to last another 100 years. In seawater, there is a pseudo-steady state chemical balance that exists between the rocks and the water. This is true of all rocks and water on land. Uranium is constantly leached from the riverbeds and carried into the oceans. This balance of uranium concentration in the seawater is about 3.3 parts per billion. The concentration is not pure uranium, but rather uranium dioxide. Then, when uranium is extracted from the seawater leaches uranium from the rocks to replace it. The uranium dioxide, when in the presence of oxygen, will actually oxidize to form triuranium octoxide, or what we generally know as yellow cake. The 3.3 parts per billion concentration of uranium dioxide in seawater means that after we apply this to the ocean volume of roughly 350 million trillion gallons, we can calculate that there is at all times a value of 4.5 billion tons of uranium available. When we apply this with the concentration of uranium in the rock, we can calculate that there is still 100 trillion tons of uranium available. Just the uranium currently in the seawater is enough to power 1,000 megawatt reactors for 100,000 years. At this volume, we would never be able to lower the concentration of uranium in the seawater over the next 1 billion years, even if 100% of all power generated across the globe was nuclear. Currently, there is considerable research being done, as mentioned earlier, on the extraction of uranium from seawater, most significantly by Japan, China, and the United States. The most recent technologies to emerge from the Department of Energy, the Pacific Northwest and Oak Ridge National Laboratories, use polyethylene fibers coated with amidoxine. These fiber braids are about 15 centimeters in diameter and can be several meters in length. Amidoxine is an organic compound derived from hydroxylamine and is used as a reducing agent. The amidoxine is used to attract the uranium dioxide to the fibers and allow them to bind tightly to the fiber surface. Each of these fibers can bind approximately 6 grams of uranium dioxide per every 1 kilogram of fiber submerged, and this can be done for up to 50 days. Then the fibers must be pulled to the surface where they must undergo an acid treatment to break down the aminos in the amidoxine to recover their uranium dioxide, and which also then allows the fiber to regenerate for future use. Currently, the implementation of this method costs about 200 pounds of triuranium octoxide, which is about double the current commercial mining cost. From 2011 to 2016, the Pacific Northwest and Oak Ridge National Laboratories were able to reduce costs by a factor of 4. As of late 2018, experiments have begun with an acrylic yarn coated in amidoxine. This base substitution is intended to further reduce the costs, but empirical data is not yet available to its success or not. With the fluctuation of the triuranium octoxide spot price from $10 to $120 over the past decade, this technology needs to be reduced to below $100 per pound to be considered a commercially viable replacement. Extraction of uranium from seawater can not only be the key to making nuclear energy renewable, but will certainly help protect the environment from contaminating areas like this and keep them looking like this. Now that we have discussed a more renewable way to acquire our nuclear fuel, we are going to discuss what we do with our fuel and how we propose to utilize it. As discussed earlier by Josh, a thermal reactor is basically a nuclear reactor in which nuclear fissions are caused by neutrons that are slowed down by a moderator. A light water reactor is just a thermal reactor which utilizes normal water, as opposed to heavy water, to act as both coolant and neutron moderator, which comprises the majority of reactors in the United States. As of August of 2018, there are currently 60 commercially operating nuclear power plants with 98 nuclear reactors across 30 states that generate an amazing 20% of power. About 27 tons of fresh fuel is required each year by every 1,000 megawatt nuclear reactor. Given this, we can crunch some numbers and figure out that we require about 208,000 kilograms, or 208 metric tons, of natural uranium for every 1,000 megawatt reactor. In a nuclear reactor, the nuclear fuel used is required to have a much greater concentration of the uranium-235 isotope than is normally found in natural uranium. Uranium-235, when concentrated or enriched, is fissionable in light water reactors. Commercially, the uranium-235 isotope is enriched from 0.7% concentration to a concentration of 3 to 5%, and only then can be further processed into fuel. The enrichment process involves using our supply of uranium oxide and converting it to uranium hexafluoride, because fluorine has only one natural occurring isotope, thus does not contribute to weight differences in the separation process. And second, because it exists as a gas at the needed low operating temperatures at a separate conversion plant. Depleted uranium is what is left over when most of the highly radioactive isotopes of uranium are removed for use as nuclear fuel. Depleted uranium is a heavy metal that has chemically toxic properties and is slightly radioactive. A common misconception is that radiation is depleted uranium's primary hazard. However, depleted uranium is approximately 40% less radioactive than naturally occurring uranium. Depleted uranium does emit alpha and beta particles as well as gamma rays. This does not pose much of a health risk though, as the alpha and beta particles are blocked by the skin and clothing. The gammas are such low energy they also pose minimal risk. Until now, the uses for depleted uranium have primarily been only of military use in ordnance and armor due to its high density. Now we have discussed the reactors that burn the enriched uranium and why the enrichment is necessary and how. We have also discussed the byproduct of that enrichment process, depleted uranium. The next component of this puzzle is the proposed means of fuel consumption, and that is the use of fast reactors. The major difference between thermal reactors and fast reactors is the extent in which they can burn uranium. We have discussed the low concentration of the isotope uranium-235 in natural uranium that requires enrichment by thermal reactors, which are then able to convert only minimal portions of the uranium-238 to plutonium-239 before their neutron availability becomes too low. As a result, light water reactors are able only to fission about 0.7% of all uranium that is mined. The fast reactor, however, are able to convert uranium-238 to fissile plutonium-239 or fission the uranium-238 directly. Additionally, they can carry an added benefit of being able to create significantly more fissile material than is used. Thus, fast reactors are able to fission practically all uranium as it is mined. Even if fission products are never chemically removed from the reactor, they can still fission up to 50% of the material. Another of the major differences between thermal light water reactors and fast reactors is the coolant. Light water reactors use regular water as a coolant, where the fast reactors utilize more exotic coolants such as a liquid lead bismuth alloy, a liquid sodium or chloride, which is currently the most prevalent, and gas coolants, primarily helium. The proposal then is that we will use the current waste as fuel for the fast reactors. As you can see, there are two graphs comparing the radiotoxicity of the spent fuel and their half-lives. On the left is the graph of our current waste materials. Note that fission products decay below natural uranium in approximately 500 years, and the actinides roughly 10 million. The graph on the right is of the same components after being spent in a fast reactor, and the values and magnitudes different, with the fission products dropping below that of uranium in about 50 years and the actinides 7,000 years. The fission products of uranium being mostly isotopes of iodine, cesium, strontium, xenon, and barium. The actinides are the long-lived particles having major impact on geologic repositories such as plutonium, neptunium, samarium, and americium. Notice also the starting energy levels of the and the actinides are drastically lower. The traveling wave reactor is the first of two fast reactors we will touch on to consume our current waste. Unlike light water reactors, traveling wave reactors are capable of utilizing depleted uranium. The core design gradually converts the fuel through the nuclear reaction and fuel shuttling. The traveling wave reactor is similar to other fast reactor designs, predominantly that the coolant material is a liquid sodium. This core also includes a special design where the breed-burn wave does not move through fixed core material. Instead, a standing wave of breeding and burning is established by periodically moving core material in and out of the breed-burn region. This movement of fuel assemblies is referred to as fuel shuffling. This fuel shuffling operation is expected to take 1 to 2 weeks, depending on the number of fuel assemblies requiring shuffling. Fuel shuffling accomplishes three important functions. First, it provides a means of controlling the power distribution. Second, it manages the excess reactivity with the control rods. Third, it greatly extends the life of the reactor core because core life is largely determined by the number of depleted uranium assemblies available for shuffling. Fuel shuffling does not involve opening the reactor because all shuffling operations are conducted with equipment installed in the reactor vessel, and it occurs at about the same interval for the life of the core. The final of our two fast reactors is the molten salt reactor. In a molten salt reactor, the uranium floats in a stabilizing bath of melted fluoride or chloride salt. As the fission process begins, the temperature slowly increases to 1300 degrees Fahrenheit. Tubes on the side of the core carry the heat to a heat exchanger where intermediate pipes carry heat to another so the energy can be transferred to the energy conversion system free of radioactivity. One of the major attributes of the molten salt reactor is the liquid fuel, because it can be processed during operation. This means that fission products can be removed from the core quickly before absorbing the neutrons, allowing for a much higher fuel efficiency than traditional reactors. Also, this means that when thorium absorbs a neutron and becomes protactinium, the protactinium can be removed immediately and allowed to decay into uranium-233 without the risk of an infectious neutron loss. The greatest of the molten salt reactor risks is the production of tritium. When lithium is used in the salt for process stabilization, then tritium will be produced. A special sodium fluoroborate is used to capture most of it, though some may still escape. Well, everyone, that wraps up the presentation. So, a real quick review before I turn things back over to John. Just wanted to do a real quick recap. We covered today the extraction of uranium from seawater, the basics of thermal reactors and light water reactors, uranium enrichment, depleted uranium, basics of fast reactors, nuclear waste, traveling wave reactor basics, and molten salt reactor basics. So now I would like to thank you all for your time, and I'm forward back over to John.